Okay, we're back. We have a few trickier problems that I want to go over here. The first one involves this graph. Below is a graph of force versus displacement for a golf ball being struck by a golf club. Determine the work that was done on the golf ball as well as the ball's final velocity if its mass is 0.085 kilograms. And that's actually the approximate mass of a golf ball. So, our first question is to determine the work that's done. Again, always remember you have two ways of doing this. You can think of it as work as the change in energy, but we're not really given any information about the golf ball's energy other than knowing that if you're striking a golf ball, that energy is going to eventually, the kinetic energy is going to change. We don't have any information about how fast it's moving. Matter of fact, that's one of the things we're looking for, and we don't know what the initial kinetic energy, well, I guess we do since it's zero, it's a golf ball being struck, but we don't know enough to figure out the work by using energy. The other way we can find the work done is by using the equation W equals F times D times cosine of theta. So the work done on the golf ball equals the force on the golf ball multiplied by displacement times cosine of theta. Let's worry about that term first. Cosine of theta, let's see. The ball is struck and it goes in that direction. That's cosine of 0 degrees between those two vectors. Therefore, this is 1. Now, how big is the force and displacement? It doesn't tell us up here, but look at the graph. The force is a constant 6,000 newtons over a displacement of 0.05 meters. So we should be able to find the work done by just simply doing 6,000 times 0.05. That would be 300 joules of work was done. Now I'm going to stop there for a second before we go and find the speed because I need you to realize what this means. Look what we just did. We took a value from the graph. It was a constant 6,000 newtons. That's very important for over 0.05 meters of displacement. This is key, okay? Because what did we really do when we just did this multiplication? If I asked you to find the area under this curve here, wouldn't you do 6,000 newtons times 0.05 meters? Matter of fact, that's exactly what you would do. So what I'm trying to get at here is always pay attention to what is being graphed. You have force versus displacement. If you want to find the slope of force versus displacement, that's like dividing the force by the displacement. That's not going to get you anything. But if you find the area, that's multiplying the force and displacement values together. We know from the equation that multiplying force times displacement gets you work. Now this is a very easy case because we have a constant force. If we had something like this, where the force is increasing over time, it would be a little trickier. We couldn't just say that the force is 6,000 newtons, but what we still could do is figure out how much area is under the curve, and that would tell us how much work is done, okay? So you always have to be thinking about what might the area tell me. You can find the area by doing the y-axis multiplied by the x-axis. And if that gives you something, in this case force times displacement gives me work, then that's extremely useful. So we're going to put this over to the side for a force versus displacement graph. The area under the curve is equal to the work that is done. Always important to remember, okay? Back in the beginning when we talked about area under the curve, I said you can always test to see what area under the curve is going to be equal to by thinking about, do the y and the x-axis variables. If I multiply them together, does it give me anything important? And in this case, yes, it totally does. Now let's go back to this question. We want to know the ball's final velocity. So remember we said, what is this work going to do? It's initially going to make that golf ball move faster, right? So all this work goes into changing the kinetic energy, which means that the work goes into the difference between the final kinetic energy and the initial kinetic energy. If you've ever played golf, you know that initially the ball will be at rest. So all 300 joules of that work go into increasing the final kinetic energy of the ball. So now we simply do 300 joules equals 1/2 0.085 kg VF squared. Okay, and let's see here. So if I take out my calculator, 300, divide by a half, divide by 0.0885, and I take the square root. Don't forget that square root part, it's very important. I get that the final speed of the golf ball is a little bit over 84 meters per second. Very, very fast. The reason is 300 joules is a decent amount of energy, and if we give it to a very small object, it's got to move very fast to make up all that energy. Okay, next question. The force of friction on an 88 kilogram skier skidding to a stop is 350 newtons. If the skier comes to a stop in 11 meters, how fast were they moving initially? So let's think about what changes here. Friction is stopping the skier. So what we have, and since we say stopping, we know that KE is decreasing. But where is that energy going? Let's think about it. KE is decreasing, and energy is transformed into internal energy. But, and here's the nice thing, we can still use that same sort of equation that we've been using, work equals change in energy, because we can consider the force of friction to be an internal force, internal to the system of the skier and the snow that he's going over, because where does that energy really go? It stays with the object. The energy stays with the skier, it's just no longer kinetic energy, it's internal energy. By skiing over the snow, if this friction is interacting with the skis, it's actually making them just a tiny little bit warmer. Even though you don't think about it like that, that's actually what's happening. Because energy stays with the object, in this case, our skier. Okay, so we're looking for how fast they're moving initially. We do know that we're changing the kinetic energy. And what is doing that? There's some work done by the force of friction. Now, we know that the work done by the force of friction is equal to the force of friction times the displacement times cosine of theta. This is equal to the change in kinetic energy, so KE final minus KE initial. There's two things we can simplify here. So the angle between force of friction and displacement, the skier is moving forward, friction points in the opposite direction. That's a difference of 180 degrees. That must be -1. Cosine of 180 is -1. So we have a negative out here. In addition, the skier is coming to a stop. So that means the final kinetic energy must be 0. So look what happens. Force of friction, negative force of friction, times displacement equals -1/2 mvi squared. I've got two negatives in my problem. Guess what happens? They're going to cancel each other out. Now I simply just have to plug my numbers in. I know that the force of friction is 350 newtons. They skid to a stop in 11 meters. Skier's mass is 88 kilograms. We solve for VI. And once we do solve for VI, we see that 350 times 11, 350 times 11, there we go, divided by 1/2, divided by 88, take the square root, we see that the skier was moving at a rate of 9.35 meters per second initially. So now we're starting to see where this can be used to solve kind of advanced problems. It's not necessarily obvious at the outset what you're going to have to do. What I would really recommend doing is, as you guys are kind of at an introductory level, writing down what you know and seeing how that can be used to figure out the answer. There might be some kind of heavy thinking with this, okay? It is rather tricky, all right? Okay, let's see here. So we figured out how fast the skier was initially moving. Interesting. A boy does 3 joules of work in pulling back a 0.04 kilogram rubber band. How fast will the rubber band move once he releases it? So let's think about what's done here. We've all pulled back a rubber band. I wish I had one here. I don't see one at my kitchen table. But you pull back a rubber band and then you release it, and the rubber band will go forward, obviously. So the initial act is doing work to pull back the rubber band. How is that changing the energy? initially, the elastic potential energy of the rubber band changes. You're stretching out essentially a spring. And after that is done, after you've stretched out that spring, when you release it, that spring energy goes away and it becomes kinetic energy. So initially, the elastic potential energy increases, but then it is converted into kinetic energy. If I were to write this out as an equation, I would say something like this. Work done goes into changing the elastic potential energy, but then the change in elastic potential energy, the decrease from stretch to normal length, turns into the change in kinetic energy. The decrease, so first, the work that's done increases the elastic potential energy of the spring, but then afterwards, the decrease in spring potential energy as the rubber band snaps back increases how fast it's moving, the kinetic energy. So let's figure out first, and we could do this in a number of ways, let's figure out first just how much potential energy was stored. So let's just focus on this for right now. The work done is equal to the final elastic potential energy minus the initial elastic potential energy. Initially there was none. There was 3 joules of work done. So the final elastic potential energy was 3 joules. Now, if we had the spring constant of the rubber band, we could figure out how far it was stretched, but we don't have that. But we don't need it. Because the idea is when the rubber band is flung, when it's released, all that energy that was stored as elastic potential energy becomes kinetic energy. So, if all final elastic potential energy gets converted into kinetic energy, then we have something like this. The final elastic potential energy is equal to the change in kinetic energy. We know that there's no initial kinetic energy. It wasn't moving before we released the rubber band, so that's 0. So what we have is the final elastic potential energy equals 1/2 mvf squared, the final velocity once the rubber band is released. So we have 3 joules equals 1/2. The mass of the rubber band is 0.04 kilograms, vf squared. I solve for vf. Okay, so 3 divided by 0.5 divided by 0.04 equals 150. Take the square root. I get 12.25 meters per second. Okay? Again, this sort of stuff is kind of tricky. It's all about just trying to make those connections, and it gets easier as you go. Okay? The more you do this, the easier we'll get to see those energy transitions. My last question. 100 joules of work is done as a 3-kilogram cart is pulled a distance of 5 meters up a ramp that is inclined at 30 degrees. How much of that work was done to overcome friction? Whenever you see this phrase, overcome friction, what it really means is how much internal energy was generated. The reason it means that, if you're trying to overcome friction, imagine if there was no friction, you wouldn't be generating any internal energy. If there is friction, you are generating some internal energy. We want to know how much energy had to be generated, how much energy had to be used. So, in this case, we're pulling a distance of 5 meters up a ramp inclined at 30. Okay, so we have, this is the situation. We have a ramp, it's inclined at 30 degrees, and we're pulling it 5 meters up that ramp. Okay, 5 meters up that ramp. But what we really want to know, you guys know that one of the things we need to know, because clearly what type of energy is changing if you bring something from here up to here? The gravitational potential energy. So PEG changes